So it's my pleasure to introduce our first speaker of the year. He's I'm going to try my best here. Sorry about that.
I'll help you out.
Niranjan Balasubramanian.
Manian.
Oh.
They're pretty close. One syllable.
Thank you for being here with me. He's an assistant professor from Stony Brook University, where he works on natural language understanding. So he's trying to read every document in the universe and make sense of them. And I guess you'll talk about what understanding means in terms of question answering and things like that. Prior to that, he was a postdoc at the University of Washington, and also one of the early members of the Allen Institute. So for those of you familiar with the Allen Institute, it's a nonprofit in Washington, basically trying to solve all the fundamental problems of AI. And so he was there to get them started on a good foot, I hope. And so, not to take much more time, tell us exciting things.
All right.
Thank you.
Hi. Thanks, Mark, for inviting me, and thanks everyone for attending. So I have a whole bunch of things. As you can see, the title is pretty long, but there's some sort of underlying theme connecting all this stuff. What I wanted to talk to you about today, can people in the back hear me okay, first of all? Good. Okay. What I wanted to talk to you about today is sort of three application or three areas in NLP. One is question answering. The other is trying to model knowledge about events, and a tiny bit about machine translation. Okay? The kinds of things that I wanted to talk about here are our forays into how we could try to reuse neural models, how we can try to decompose and put them back together in some ways to use in some target applications, and maybe how we could try to control how these neural models actually work in practice. So those are the themes that I want to touch. Sort of made this talk largely for an NLP-ish audience, so feel free to interrupt me if there's stuff that needs to be explained. I'm happy to take questions in the middle also. Okay, but there's warning, whole bunch of content ahead, so I'll try to get through as well as I can. Okay, so let's start with multi-hop QA. Okay, so I'll start with a definition by example. Okay, multi-hop QA is, I think, somewhat hard to define in language, like many other language tasks, I believe. The way I would define this is through this example. We have a question here which says, which city was Facebook launched in? And you're given as input some piece of text which contains the two sentences that are here. Okay? One conveys that Facebook was launched in Harvard University. Another one says Harvard University is actually in Cambridge. You're supposed to combine these two bits of facts and derive the answer, which is Cambridge. Right? So multi-hop in this sort of a loose sense for us is where you need to combine more than one piece of information that's in distinct places in the text, and you get an answer. Okay, that's multi-hop QA for me. So in this space, I want to talk about three pieces of work that the lab has been doing. The first one is how can we use models that have been trained to do this task that is called entailment. How can we take a model that's trained for entailment and use it for QA? Like, what's the connection? How can we do this? So this is where reuse comes in. Okay? The other bit I want to talk about is how can we get a trained model that's trained for doing question answering. How can we get it to run on a resource constrained device like a mobile device? Right? Can we get these models to run faster? If you run these models as is, they run really slow. How can you make them faster? Okay? This is where I'm going to talk a little bit about decomposing a neural model so that it can run faster. And the last one is something, it's really an aspirational at this point. We don't really have results or made a lot of progress, but I think it's an important problem in general in NLP. So we build these models. We have lots of data sets for many NLP tasks. We build these models and we get good performance on the data sets, but you really can't guarantee that the models are in fact solving the tasks that you're designed the data sets for. Okay? So in this talk, in this piece, I'm going to tell you a little bit about the difficulties of having multi-hop data sets and building models that actually try to solve this thing, but they actually are not hoppy in the sense that they don't really combine multiple bits of information. Okay, so what can we do about these? All right, so let's get started with the first bit. Okay, this is joint work with the AI2 Institute. I'm still keeping my connections to them. This is work led by Harsh Trivedi, my student, along with Hyung Kwan and folks at AI2, Ashish Abarwal and Tushar Kote. Okay, so there are these two areas in NLP. One is called textual entailment, and the other is QA. this work tries to bridge these two things. Let me again try to define through an example. So here I'm trying to define what entailment means. In a logical sense, if you're given two pieces of information, so Zuck studied in Harvard and Zuck lived in Cambridge, the question is, does knowing that Zuck studied in Harvard necessarily logically entail that Zuck lived in Cambridge? Okay? So the answer to this is probably not, right? In a strict logical sense, he could have been a commuter, but you can frame a softer version of this problem, which is often referred to as natural language inference, where you want to say, does the piece of information in one sentence give you some probable reason to believe the information that's contained in another sentence? So it's sort of a softer version of the problem, right? So this problem is typically been studied at a sentence level. So I give you one sentence, which we will call the premise, and I give you another sentence, which is called the hypothesis, and you want to say whether the information in the premise supports the information that's contained in the hypothesis. Okay, so we've developed a bunch of data sets for this. So there was this original data set called Pascal, which launched this problem in the NLP sphere. And then we had this recent large-scale data set called SNLI from Sam Bauman and others at Stanford. This is a really large-scale data set with close to 1 million pairs of sentences where you know if information in one sentence supports the other, contradicts, or is neutral to the other one. Right? So we have large data sets. So what happens when you have large data sets? You have large number of models where people throw their favorite model at this problem. Basically, all our neural models today, there's a leaderboard. We just have a bunch of choices. Okay. Let's look at multi-hop QA. Again, this is by definition. We saw this before. And there's again a bunch of data sets for this problem also. Okay, there's been some choices we have here. And again, in terms of the model space, there's a lot of choices. This really, while there is some influences in terms of architecture, what we learned from entailment have been somewhat applied to QA and vice versa. There's really not been any attempt where you say, okay, let me take a model that's trained for entailment and see if we can use this for QA. Okay? So our work basically started with this question: how can we use NLI data sets and the models that have been built to do multi-hop QA? Okay, what does it take to do this, right? And of course, the reasoning is there's some thought that has been gone into these NLI models. Can we somehow repurpose these models to work for QA? If you are pre-training on a related task, then therefore it should be helpful for this target task that you're interested in. So this seems like a reasonable thing to do, right? So the question then is, like, how do you frame a question answering problem using entailment? Okay. Basically, let's assume that we are given a question and some candidate answer, okay, and we want to check if this candidate answer is the correct answer for the question, given some textual knowledge. So you want to use the text that you have to verify if the candidate answer is going to be the correct answer. So you can already see how this can be framed as an entailment problem, right? But what we want to do is we want to build a QA model that does this job by taking a pre-trained entailment model and somehow using it to build out this QA model, right? That's our goal. So here's a simple example of how to do this, right? So I have a question. It's basically the same one. Where was Facebook launched? I have 3 candidate answer choices. Okay. The first thing I do is to create a answer hypothesis. Okay. Let's take Cambridge, our answer. Okay. And we want a QA system which would verify if Cambridge is the correct answer. And the way we are going to do this is by first translating that answer into a hypothesis, right? An answer hypothesis, which is basically Facebook was launched in Cambridge. So this is the thing that we want to verify given some textual knowledge. Okay. Let's assume that there is just one piece of sentence in our textual knowledge, which is this premise that we have. Facebook was founded in 2004 in Cambridge. So the question now, the multi-hop question now becomes an entailment problem where you're trying to verify if the information in this answer hypothesis is entailed by the information in your knowledge, which is this particular sentence, right? Just a straightforward framing of QA using entailment. However, a more realistic example looks like this, right? We don't just have one sentence. We usually have a collection of sentences, and we want to say, does the information in this collection of sentences together somehow entail the answer hypothesis that we have, right? So this is the problem that we are trying to solve. So if you have, as I said before, the NLI data sets are sentence-to-sentence data sets, and so therefore the models that we have learned are models that can take a pair of sentences and tell you whether one entails the other, right? So if you want to directly apply these models to this particular framing, right, there's a couple of straightforward ways of doing this, right? One is you could take each sentence you have in your textual knowledge and then individually check if that sentence entails the answer hypothesis, right? You make independent decisions, and then you somehow combine these independent decisions together and try to answer the question. The other thing you can do is to concatenate all the sentences you have into a sort of single piece of text, and then say, okay, does this this premise, which is basically a concatenation of sentences, together somehow entails the hypothesis, right? As you can guess, neither is actually particularly the right way to do things, right? The independent decisions basically cannot aggregate information, so each sentence may only contain partial bit of information, so you may not be able to get the correct answer. And when you concatenate text together, it's a divergence from how the entailment models are trained. The models are trained for sentence to sentence, so if you concatenate a bunch of them, they are not going to work very well. And they can also get distracted by sort of additional information in the sentence, because there is only a small portion of the text that is relevant to actually answering the question. Okay, people good so far? Any questions? Okay. When we thought about this, okay, the basic question to ask is, okay, what does multi-hop reasoning involve? So I'm going to argue it involves two things. Okay, first is that you need to somehow identify, given the set of textual knowledge sentences you have, which sentences are really relevant for figuring out the answer to this question. And having somehow softly identified which sentences are useful, you need to somehow combine the information in them and then check if that combined information entails the answer hypothesis that you have, right? Those are two steps that we need to do. And you can see that this sort of, if you squint hard, somehow you can see these are doing some weak form of entailment at least, right? So I can check if it's basically I want to have some capability that checks information in one sentence with the information in the answer hypothesis. So this I could use the entailment models for directly somehow, right? The second one is where I want to compare the information in a bunch of sentences together with the information in the question. This is the one that sort of requires a little bit more work. Okay? So what we are going to do is to say, okay, here's a way to reuse pre-trained entailment models for this task. We're going to first build what we call a relevance module, which is going to take the sentences in your knowledge and then provide a relevance distribution over them, basically just the relative importance of these sentences with respect to the question, if you want to think about it like that. And then another module, which we call the aggregator module, which is going to use these relevance weights to pick up some important information from different sentences and then do this entailment decision. Okay? So as I said before, the relevance module is somewhat straightforward to do. I'm going to apply the entailment model individually over independent sentences. Yes, I said that was a bad thing to do a few slides back, but in this case, we are only interested in sort of providing a ranking, right? Not necessarily figuring out which is the relevant answer. Okay, hopefully that ranking is still useful. Okay. And the key thing is this basically aligns with the entailment data sets, right? Because they are sentence to sentence. Here we have sentence to sentence, so this fits well. But the aggregated module, as I said, is a little bit tricky. Here, the aggregated module needs to do the following things, right? It takes in multiple sentences as input, along with the answer hypothesis that we are trying to verify. And then it needs to basically produce a representation of each of these sentences, okay? And once we have these representations, it needs to be combined into a single representation, okay? But before we do that, we want to use the relevance weights that we get from the relevance module, right? So the first step we did is we softly figured out which are the important bits of information. So we take the representations weighted by the relevance information and do some kind of a join operation that combines these things together. And then using that representation, we want to make an entailment decision. Okay, so it's a basic way to construct this kind of a module. Okay. Now, so if this entire box is actually doing an entailment function, okay, our goal is to figure out how we can repurpose a trained entailment model to do this kind of a box, right? So we're seeing that there are sort of these green and gray boxes that we have. How can we use a pre-trained entailment function to implement these green and gray boxes? So to do this, we're going to pretend that the entailment model is a loaf of bread that has been sliced, basically to indicate that the entailment models that we have today are all neural models with multiple layers, right? They do some transformations and then they do some decision making at the end. Okay, any other analogy would have worked, but Harsh really likes bread. I said we should have done a layered cake, but he disagreed and he won. Okay, so basically the loaf of bread, the sliced loaf of bread takes its premise and hypothesis and gives a decision, right? An entailment decision. Now we're going to take this pre-sliced bread, right, and then we're going to slice it into two halves, upper and lower half. Okay, the upper half is going to be our green box, and the lower half is going to be the gray box in the figure that I showed. Okay, so this basically means that you can take the lower layers of the entailment model and use that to construct a representation of each sentence, okay, this is going to be done in conjunction with the answer hypothesis. It's going to give you some representation, and then we're going to apply a join operation that combines these sentence level representations into a single one, and then we're going to use the upper layer from the entailment model that you've broken up and use it as if it's sort of it came from the original entailment model. Okay, so that's our architecture. So the lower layers are applied sentence-wise, and the upper layer is applied paragraph-wise. Okay. And of course, we're going to use the relevance weights to scale the sentence-wise representation so that the upper layers can consume this. Okay. But why slice the bread in only one place? We can slice it in multiple places. Who knows what these neural layers are capturing? Each layer is doing different kind of stuff. So you could potentially slice the entailment model in multiple places, and whatever resulting representations you get, you can concatenate them, and then you can throw them together. Right. So that's our full aggregator module. So given this, the entire model that we have is as follows. So we have the relevance module, which is using the pre-trained entailment model to produce sentence-wise relevance weights. And then you have the aggregator module, which does this weird slicing thing and joining stuff together. And then we do the entailment. Okay. So we call this model multi. The acronym is mine. The expansion is my students. Multi-layer aggregation of textual entailment representations. Mouthful. Okay, so to sort of finish the description of this architecture, I have to tell you two things, right? What is the entailment model we used, and what do we do with the join operation? We didn't do anything spectacular here. We took a model that was called popular then. It's called eSIM. It's basically a bi-LSTM based model. It takes each sentence and runs a bi-LSTM over it, gets an encoding, and then it does this thing called cross attention. Basically, every token in the sentence is compared with every token in the answer hypothesis. And then you get an attention matrix, and that is then used to somehow produce a combined representation, which is then used to make an entailment decision. Okay. So sort of basic architecture for doing entailment. We slice this model in two layers. One is at the cross attention layer, and one at the higher layer. The join operation is actually quite straightforward. In the case of cross attention, basically the cross attention layer outputs a matrix. Okay, so an attention matrix that tells you the importance of each token with respect to each token in the answer hypothesis, right? So this, you get a sentence level attention matrix. You need to somehow combine it and produce a paragraph level attention matrix. And these attention matrices are now weighted by the relevance weights, right? Based on the sentence from which they come from, we get a relevance weight for that sentence. So we basically multiply each element by this weight, and then we do some normalization, and you get a paragraph-wise output. Okay, so nothing special. Here's a basic way to accomplish this. Okay, so in terms of evaluation, as I started by saying, the direct ways of applying entailment models is suboptimal because they have weaknesses. It turns out that indeed in practice they don't do that well compared to multi. Multi does much better. We also evaluated multi against other larger transformer-based models. So remember, our entire QA model is just made from repurposed eSIM, right? That's all we have. So we compared it against larger transformer models that were pre-trained on language modeling tasks, and then fine-tuned on multiple question answering data sets also. So here are the results. For one data set, which is called OpenBook QA, the model does better than the OpenAI transformer, which was the best model at that point. And then contemporarily, we also had another transformer model, which was trained on this data set called RACE, which is a large question answering data set. Again, these are much bigger models. Our eSIM based model actually does better than or comparable to the ensemble based version of the reading model. Okay. A similar story exists for another data set called multi-RC also. Basically, there are sort of two takeaways for me from these results. It's just that you can take entailment. The entailment data sets are actually useful for doing QA. Taking pre-trained entailment models here actually can be helpful for QA and comparable to large models. Okay. So there's really nothing in this architecture that says you can only use eSIM, right? What we showed is if you have a model that has some layers, you can divide this model into two pieces and somehow use it. So we could use BERT, for example, or any other large transformer you have, and do this kind of a model also. we are working on this. We don't have results yet, but hopefully we'll have something soon. So the interesting thing with respect to BERT or any other language model at this point for me is that it might be the case that for many tasks that we have, the training data you have is easier to get from a sentence level or shorter context. Okay, so if you want to take a data set which is defined over shorter context and you want to apply it for another task where the context is longer, maybe this is a way to do that kind of a transfer or accomplish that transfer. Okay. Right. So I basically said those two takeaways. Any questions before I move on to the next bit? Yeah.
Does it have to have the same number of stacks as the number of points of evidence you have? So if you have 4 sentences, it has to have four inputs, or is there some sort of more flexible or recurrent way to do that?
We hadn't thought about a recurrent way to do that, but at this point we just so we don't have different. So for the lower layers we use this we use the same module to produce a representation, so that we are not duplicating parameters, for instance, right? So there's no, we're just reusing the same model. There is a loss of so in some cases, for example, if you're thinking about a paragraph and the sequential information, so if you don't process them together, there is definitely some loss of information. You could think of a recurrent model in those settings to see if that could be addressed. Yeah, that's a good point. Yeah.
So does this model scale well comparing to using knowledge graph?
Comparing to knowledge graph.
So if you use attention mechanism, I believe it's like a square. I mean, if you double, you have 4 times processing time, and probably in knowledge graph it's like that too. Is it going to be faster?
I'm not sure I see the connections clearly. So, so are you saying that we take the text, construct a knowledge graph out of it, and then figure out how to answer it based on this kind of a model?
Yeah, yeah. Do you have any thought about comparing? These two.
Right. So we haven't thought about this, but in general, the kind of problem the interest that I have is I shouldn't say interest. There is definitely a loss of information when you go from text to a knowledge graph, right? So increasingly what we are seeing is sort of treating, trying to encode text as a whole, but then when the text becomes much larger, right? Like I have to, let's say, I have to do a Google search to get a bunch of documents, and then I have to reason through a whole bunch of documents and then give an answer. Maybe a knowledge graph setting might be useful, but I hadn't thought about this. Okay.
Thank you.
Yeah. All right. So I want to move on to the next bit. It's basically trying to take again a pre-trained model, okay, that's been trained and developed for, let's say running in commodity devices, and how can we get this model to run on a target environment which is different from the environment that it was originally trained for, right? Like let's say, what if you want to run these models on mobile devices, right? The models are at this point are really big and they have a lot of compute, so it's really hard to get them to run. So if you want to get these models, let's think of an end-to-end question answering system, right? I have a large collection of documents, I have a question, I want it to be answered. Okay? There are 2 sources of bottleneck in terms of compute, right? 2 things that contribute a lot to the compute. One is the number of paragraphs or documents that I pass through my QA model, okay? And the amount of compute that my model does on each such paragraph, right? Both are things that we want to reduce. So we had some initial work that basically said that if you want to do on-device evaluation, basically if you have a mobile device where you're doing this end-to-end QA system, current models take as much as 80, 90 seconds to answer a single question, which is really terrible. Like these weren't even BERT-like models. Okay, so these were older models. If you have to process, let's say, 150 paragraphs, that was the optimal size to process to get the high levels of accuracy that we wanted. So if you want to process roughly 150 paragraphs, it takes a minute and a half. Bad thing to do. So one thing we said is, okay, can we try to optimally decide, given a question, how many paragraphs to process, or even better, as we keep processing the paragraphs, can we decide to stop early, like that we know we have gotten the correct answer. We can do tricks like this, and we can actually get it down to about 5 seconds or so. Okay. The other thing that we are currently focused on is trying to reduce the compute that you do per paragraph. Right. Let's assume we are now in the world of we're given a paragraph, I'm asking you a question, but I want this to be running on my mobile device, right? The current models that we have are really huge. They don't even fit on the phone, but let's assume they can fit with some tricks. It's still, they take a lot of time to run. Okay? So we have some ongoing work where we are focusing on this idea of decomposing a pre-trained model so that it can actually run efficiently on a mobile device. So some copy-paste failure. Okay. Right. So this is the slide I wanted to be. So one thing we could do, right, is to do model compression. Right. I have a huge BERT. I can compress the BERT, and smaller model means smaller, lower amounts of compute, and hopefully that can run faster. It has memory benefits, etc. Right? Turns out it's a bad trade-off, at least as of now. Right? The idea is there's a model called distal BERT. At least at the time we looked at this, there's a high loss in accuracy when we apply it to the QA task. So there are models that can be, the BERT can be compressed to a smaller model. It works well for the language modeling task and some of the other sentence level tasks, but for QA, this seems like it introduces a high loss in accuracy. And you actually have to, in many cases, do the pre-train the models. Okay, so you take BERT, and if you want it to be mimicked by a smaller BERT, then you have to get the smaller BERT to do the same language modeling task, right? So this is not a place where you can explore design choices. So let's say I want to compare the trade-offs of having the model size versus accuracy, then there are many such models I need to do, and it's not the easy way to get at this, right? So one thing that we looked at is to see, what is the main source of bottleneck or compute, main source of compute in these models. Okay, in the transformer-based models, right, they look like this, right? This sort of bunch of layers. They don't exactly look like this, but sort of. Details gone. Some layers like this, right? In each layer, we basically have to compute the representation of each token in the input, right? By comparing the representations of all the other positions, right? So basically you have n squared complexity if n is the length of your input. So if I think about a passage and a question, so denoting P and Q, right? Then I'm basically computing O of Q plus P the whole squared is my complexity, right? This is basically saying that if I'm computing the representation of a passage token, I have to consider the representation of the question tokens also to do this, right? So you probably guess where this is heading. A question to ask, is it necessary that we do the whole input-wide attention in all the layers in a transformer, right? It may not be necessary. To some extent, you can look at a sentence locally and say, okay, I can understand this, right? Why do I need to look at things that are far away to make an understanding of this? At least at the lower layers, maybe I could just get local representations at the lower layers. Maybe at the higher layers, I could get input-wide representation. That's a way I can reduce compute, right? So we did this small experiment to check if this is in fact holds. Right? What we did was we took a question and the corresponding passage you had for that question, and we computed a representation. Right? At each layer, you get some representation for each token in the passage. Right? Now, if computing the passage representations has to necessarily depend on the question, then if I change the question completely to something else, then this passage representation should change quite a bit. Right? So what we checked was we basically looked for this trend that there is a higher variance in the upper layers than in the lower layers. So if I change the question, the lower layer representations didn't change as much. And granted, this is sort of reading a bit of tea leaves, checking vector representations, et cetera, but the trend is sort of what we thought we would expect. That if you change the question, that the representations that the higher layers produce is much different than the representations that the lower layer produce, right? So we basically figured that local attention might be enough. So we did this simple decomposition. We're basically saying we're no longer going to compute this cross attention. Okay? Each layer, we're going to have the passage representations computed by attending to only passage tokens, question representations only by question tokens, and then at the higher layers, at some layer that we decide, okay, we are going to do the regular thing, right? So this is, again, we are taking a pre-trained model, right, and applying it in this way. This is a divergence from how the model was trained, right? So basically, the thing we get more than the savings in compute, right? So here you basically get O of Q squared and then O of P squared, right? That's the complexity wise, okay? But the bigger savings that we get is actually now the passage computation is independent of the question, right? Which means I can pre-process all the passages and then cache them, and then I just look them up, and then I get I just need to feed them at the top layers, right? So that's the biggest benefit we get. So we can cache and reuse. And even though this is a divergence, right, the model architecture is largely the same, right? There's nothing that I've done. So this is not a drastic change compared to what model compression does, for example, right? Going from 12 to 6 with fewer attention heads, etc. So the architecture largely remains the same. Therefore, the pre-trained weights that I have are largely okay. So I just take the pre-trained weights and I do some fine-tuning on the target task. I'm already in a good space. I only lose about 3 points in accuracy on a target question answering data set. Okay? But even this we can improve by doing the sort of what is called as knowledge distillation or distillation ideas. Okay? So, right, so we want that model, right, which is our decomposed model, right, which is much faster, to behave exactly like this model. Right? So in layer k plus 1, whatever it's computing, right, it's now should look exactly like what this layer k plus 1 is computing. As long as it looks closer, maybe I'm not losing a whole lot of information. So I could add some additional losses to my objective, which are called as distillation losses, during fine-tuning, okay, that can even mitigate those small losses that we get. Okay? So this is a simple way to further improve the performance. Okay? So I have some results here. This is just showing how to decompose BERT. We get about 3.5 times speed up. In terms of runtime, we get around 70% reduction in memory usage because you're not keeping the representations of the lower layers around anymore. You only need to pull the kth layer's representation during runtime. Okay, so you get a large savings in memory also. We have results with XLNet, which look similar as well. There's also some numbers in the bottom rows that are talking about sentence-to-sentence models. You can pretend if one sentence is already given to you, then how much savings you get. You get roughly about twice. Okay? So basically, the broader takeaway in this thing is that you could actually, so the models that we use in NLP today are getting bigger and bigger. If you want them to run on mobile devices, something needs to be done. Doesn't mean that we actually have to give away or throw out this sort of benefits you get from having multiple layers of transformations, right, with many heads. There are possibly ways to sort of do some small changes to the model. Decomposition is one such idea, but still retain the model structure and still be able to do well. Okay? So this kind of disassembling and putting things back is useful. The other main message here is that it's really important to understand the bottlenecks in compute. So if you're doing it on other devices, there's non-intuitive systems, things that crop up, and some of these changes don't really work very well on mobile devices. So it's really critical to understand from a system standpoint what is causing the bottleneck. Okay. The other thing is, again, this notion of, do we need to have full input context-wide processing for all tasks? I don't think it's a sort of a settled thing. We might be able to, depending on the task, you might be able to pick up local context processing alone and then sort of assembling these local context representations at a higher layer to do interesting things. Okay. Any questions on this? Yeah.
So in the last slide, where you basically break the last layers into two, and the idea is that the question part is the one that changed, and the part which is on the left remains the same. That's why you can pull it, right?
Yeah.
So means the right half, layer k to layer 1, which is basically getting the question. That is something you have to pull completely. It's just that layer k to layer 1 on the left is what you can optimize. You know what the value of them, because they are independent of them.
Yeah.
And that part is basically giving you less memory and more. More.
Yeah. So it's the ability to cache that's the biggest savings here, right? So this is not, yeah. So this idea, I mean, there is some runtime savings there, as I said. Instead of O of, so you lose the 2pq, right? O of q plus p the whole square. That was our complexity. But here this model has O of q squared and O of p squared. The 2pq is gone, but that doesn't actually practically give you a lot of savings. But the p squared is now replaced with a constant because I can just look it up. That's where the big savings comes in.
Directly will get to layer k plus 1.
Yeah. Yeah.
Are there any experimental results on accuracy-related metrics after this approach was undertaken?
Yeah. So I'm sorry. I have a tendency to skip through things. So if you look at the BERT base and decomp BERT base, the second and third columns, so there is a small drop in accuracy. right? But it's like 1 point something. Yeah. Okay. So this part, how am I doing on time? Okay. So this part, as I said before, is something that I'm very excited about. But there is really, this talk is mostly aspirational. Okay, so we don't have lots of direct results to talk about. Okay. So we're again focusing on multi-hop problem now. So basically, by now we know the story, right? Data sets come out, okay? And there's a lot of progress. There's some leaderboard out there people put out, and there's suddenly a whole bunch of models, and there's some leaderboard frenzy, but really this does not indicate that we've made progress on the task. Okay, this has happened in multiple areas, including some nice results from here on VQA, right? Essentially what happens, right, we create data sets by going to crowdsourcing, right? So we give people a large text and ask them to create questions that we hope tests for multi-hop question answering, right? That basically gives you a quality data set. Okay, so you get question answer pairs. But the assumption is that these data sets, in these data sets, that actually for each question more than one fact is actually necessary to answer this question. This is some assumption we make about the data set. And all the core facts that were necessary to answer the question is part of the input. Okay. So I should say, I mean, the data sets are like this, right? You have a paragraph. This is the paragraph that a system should read, and there is a question given to you, and then there is an answer given to you, right? So the system should read this paragraph and the question and give you the answer. A good data set, right, is where this paragraph will have two facts somewhere, right? That at least two facts that need to be combined in order to arrive at the answer, right? This is the hope that we have. Okay. So the hope then is that when models are trained on this data set, okay, they will actually use the information in the input text and will actually learn to do multi-hop reasoning. Okay. But this is, this is not always realized, this hope, right? Why? Because models can exploit shortcuts that exist in these data sets in terms of reasoning and any other artifacts that exist, and basically solve the problem without actually doing multi-hop reasoning. Okay. There's been a bunch of papers on this recently. A thing that we can ask is, okay, what do we do in these kinds of settings, right? One thing we could do is to carefully study the model behavior. Let's say you have a data set, you have trained your favorite model, you carefully do some control experiments and see if the model does the right thing. Okay, so you can try to understand whether the model is doing multi-hop reasoning. And then you can say, okay, now that I've understood the kinds of cheating that this model does, let me go back to my data set creation and then fix my data set creation so that this kind of cheating can't happen, right? So I create harder questions where this cheating will fail. The other thing we could do is to think about some clever ways of evaluating these models so that they're not just evaluated on question answering accuracy, but instead you ask them to say, okay, which are the bits of information you used to derive this answer, right? And then you might have marked up, okay, here's sentence 1, here's sentence 2, I used these two to give you the answer, right? Now, you can't really trust the models when they actually do them, but that alone is also turns out not to be enough, okay? So when we looked at this, we said, okay, really going back to the data set and having people give us harder questions is really difficult, right? Just getting questions and answers that are consistent with the passage itself is hard. To ensure that these questions require multi-hop reasoning is not something that we can easily enforce and get data at large scale. So one thing we want to do is to say, okay, can we take existing data sets, okay, and somehow transform them so that we can guarantee that a model cannot do well on this data set, this transformed data set, unless they actually do multi-hop reasoning. Okay? So this is our aspiration. So we have basically two goals. One is to create such a data set, and the other is to be able to have some kind of a measure that tells you, you give me a data set for multi-hop reasoning, and I will tell you how much actual multi-hop reasoning your data set requires, or you give me a model and then I will tell you how much multi-hop reasoning your model does given a particular data set, right? These are really hard goals to have, but that's sort of what we are looking at. So the basic idea behind our transformation is something like this. So I give you a question, and then you have these two facts that I already know should be combined to answer that particular question. If I remove one of these facts, okay, then a basically a hoppy model, right, the model that does multi-hop reasoning, should return or should fail, right? It should not be able to give you the correct answer because it doesn't have the information to give you the right answer, right? A non-hoppy model, on the other hand, something that uses some kind of a shortcut, right? So an example of a shortcut, right? Which city was Facebook launched in, right? I had 2 pieces of information, right? If the model is using a shortcut, it could say, let me look for a city and return it. I don't care about Facebook or anything else, right? That's the kind of shortcut that we want to avoid. Okay, so a non-hoppy model which uses this kind of shortcut, right, will still return the same answer because it was never using that first sentence in any way, right? Okay, so this seems like a reasonable idea. So we can take any question that you have in your original multi-hop data set and create a parallel question, right, where we remove one of these facts and replace it with something else, and now we create another question where the answer should be unknown, right, or I don't know what the answer should be, right? So what we can do then is to create an evaluation measure, okay, which we call paired accuracy, which is basically a model gets 1 point if it answers both versions of the question correctly. For the question, when we give the full input, it should give you the right answer, and then when the question with the modified input, it should give you the answer I don't know, right? Only if it does well on both does it get 1 point. Okay, so to demonstrate this kind of thing is actually reasonable. 5. Okay. Right. So we can take a model like BERT, and we can basically show that you could run this model in a single fact mode, meaning where you're hiding some of these inputs, and then ask the model to combine its decisions. And you can basically demonstrate that on this transform data set that we have, the BERT model, when it runs on the original data set, right, in a single fact mode, can actually get as high accuracy as possible, but on the transform data set, it actually gets 0, right? So this is the kind of result that we want, although I sort of show an empirical point here that this is actually possible. Conceptually, there are lots of holes in this kind of transformation. So sadly, we can't really guarantee that this kind of transformation alone, okay, will guarantee that no model can do just single fact reasoning and get a non-zero score. So it is not possible to actually get this kind of behavior in theory, while in practice it might actually be possible. Okay, since I have about 5 minutes left, I'm going to try I'm going to switch gears and just talk about a little bit about multi-hop, machine translation here. Okay. Okay. So I talked about reuse, a little bit of decomposition, right? And this attempt at multi-hop reasoning is sort of our attempt at trying to get control, right? So we want the models to behave in a particular way, not just get good accuracies on the data set, but we want them to actually do multi-hop reasoning. Okay? So we also did some work in machine translation where we sort of try to do a little bit more control. So in machine translation, usually you have an input that goes in one language and you want to translate and produce a sentence in the other language, right? So what if I wanted to have more diverse set of translation? So I want the translation to be controlled in some way, not just faithfully translating the meaning, but I also want it to be written in different forms, let's say. So one angle we were looking at is, can we ask the decoder in the translation model to take as input a part of speech tag sequence and then translate the input into that part of speech tag sequence in the target language. Okay? So we have a latent variable model that does this. The key challenge is that when you introduce latent variables in your decoder, right, you're basically at the mercy of inference tractability, right? So you can't basically, if you have a latent variable and then a target output that you're trying to generate, you have to marginalize over all possible latent sequences, and that's really expensive to do. Okay, so what we did was we took a simple approach of decoupling the dependence between the sequential latent variables, and instead said we have the latent variable that's going to correspond to part of speech tag sequence, and conditioning on it, you're going to generate an output. But the next step, the latent variable's value, is only going to condition on what we've generated so far, but not on the previous latent variables. Right? This decoupling means that now we can actually do this kind of inference efficiently. Okay, so we can actually exhaustively do this. So what this model basically gives us is a way to explore the latent space more exhaustively, and we can decode out from these latent spaces into the target into the target language. So basically, we get better translation, we get a better exploration of the latent space, and given some particular set of latent values, maybe a part of speech tag sequence, this model produces better translations that sort of more adhere with the input that we give. Okay. So I'll skip details of this. I'll stop there and take questions. Yes.
So like we are doing this multi-op. I want to know what is the performance on the single op questions. Like how are the state-of-the-art model does on the single op questions in which you just do not have to do.
Right. So. So I sort of initially gave a punt, right? So it's not clear to me how to define what a multi-hop question is in some sense. So it's actually by implication, it's harder to define what a single hop question is either, right? Assume, let's say, a single hop question is one where you have a single sentence, okay, which is all you need to answer that question, right? The data sets like Squad, for example, they might contain a mix of these multi-hop and single hop questions, so we don't really know the performance. But if you go by, let's say the performance on Squad is kind of a, I would say it's a lower bound for the performance in the single hop questions, assuming that single hop questions are easier, right? So these models get close to 85, even 90 sometimes in these data sets. But there again, it's not clear if the models are actually doing the right reasoning to arrive at the answer or just exploiting some kind of a spurious correlation or shortcuts to come up with the answer.
A high-level question. Seems like a lot of what you are working on involves really identifying these bottlenecks in neural nets. And I think it makes sense when you're talking about mobile devices because you're limited in terms of computation. Are there, I guess, I feel like a lot of people don't think about bottlenecks in the neural nets and the computational cost and the big O's and that sort of thing. And so I guess my question is almost like computing local on mobile or small or like lightweight computational devices versus cloud, where in some sense Google's answered everything. It's just do everything on our cloud. We'll just make everything bigger. I wonder if you just kind of thought about like where these large neural networks are going and which is the path that you think will be successful.
Yeah, I think so. I don't necessarily. So I think there are two ways to think about this, right? So one is I have some target environments where compute is a bottleneck, and I need to figure out how to get these models to work well there. But even on the general setting, right? So if I could do inference faster, at Google scale, if I want to serve Google search queries using my models, I better be faster, right? And especially if the trained models that we have now sort of tell us that I don't need to process the entire context, it's just hugely wasteful, right? And the other side effect of this is you might actually get better training effectiveness because you're now able to train over more samples than you spend more time. So I think there's a whole lot of benefit there apart from the other things about carbon footprint and etc. There's also implications there. There's another side to this is to sort of thinking about bottlenecks helps you, just trying to be efficient helps. I think this idea of throw more compute and more resources is one direction. I think that should be explored. But I think there's value in thinking about constraint settings or settings where you say, okay, what is the chief bit of information I need to do something? I think that tells you a lot about what you need for the task. For general science, I think that's useful still. Yeah, I think I'm also interested from the side of or these. I think I'm becoming a little bit of a control freak. I sort of want to know what these models do. I want to control what they do. I want to understand them better, etc. And I think with bigger models, and it's getting harder. Right.
Do you think it's actually easier to debug when they're kind of split and spliced in various ways? So, I mean, like some of the models, you're just kind of breaking weights, right? You're just removing weights from models. And does it help?
So,
How does it help understand?
I think in this case we don't actually remove weights.
Okay.
We only we slice the input and sort of compute them and put them back in. In the previous case, yeah, we don't change any of the weights, but yeah, the first work is sort of like that. We've now constructed something with parts from other stuff, but it's remarkable. I don't know what to say of this. Like, there's just few epochs of training, and then this model seems to settle down. So I think if you stay, again, I think it's crucial to stay as close to the original architecture as possible. Then good things seem to happen. If you've changed it to a completely different architecture, then it's tricky. So one thing that we struggled with was position encoding. So if you give position encoding for one and the other, and then the top layer somehow needs to resolve the position encoding, there's some tricks that we had to do, nothing particularly clever, but that was difficult. So we didn't. So for example, we found that. So if the answer was located in a particular place in the passage, the model would always sort of say this is the answer. And it was sort of almost clear just looking at where it was placing. It was always close to the exact answer, but picking random tokens of different type. And that seemed like, okay, there's something funky going on with the position encoding. So we were able to debug that right away. But there are really weird phenomena like this that can happen. There was a question. Yeah.
In the hot QA data set, it says that it's a data set that's kind of also focused on generating explainable sequences. A lot of the kind of more social science explainability criteria coming in is asking for explainable AI to also have some kind of way to propagate consequences of explanations back onto the models, and it seems like your splitting technique is one that actually work. Have you guys tried or considered varying where the model is split based on the quality of like this I guess top or not?
So yeah, so we've varied the places where we can cut the model to see if there is a trade-off. I think we picked 9 because that seemed like the right layer to cut from an empirical standpoint. But this the explainability idea is actually pretty cool. I think it's a way to try to understand model behavior in some way. So I'm interested in explainability for its own sake, not just in application to this particular thing. So we have some ongoing work, rudimentary work on relation extraction, where we're trying to produce relationships between drugs and diseases as mined from biomedical literature, but alongside spit out why we think that's the case. And then the question is like, now can you take the explanations back and feed it to the model again, change the explanation somehow, and see if the model now gives you a different result? Because if it is actually using the explanation, it has to be consistent with its decisions using the explanation. But that's not really related to this, but that's a good point. Yeah.
So I think ways that we understand neural networks a lot of the time is through information bottlenecks. I'm not sure if Art was talking mainly about computational or about information bottlenecks. I mean,
All right, that's, yeah, I should have clarified. It was in my mind. Please go ahead.
But and I don't mean that in like the formal sense. I mean that in a more vague sense.
Yeah.
Like there's a bottleneck in the locality. So you can talk about locality because you know that this
Right.
information must be consumed with this input. So is that and so you say you're interested in like you're frustrated with neural networks and being able to understand them. So is that level? I feel like that level of understanding is in some sense unsatisfying because it's still sort of vague. I only know like which information is where. I don't know sort of exactly what's going on with it.
Yeah.
So like what opportunities do you see to go beyond that? And is that enough? Like what are your thoughts on that?
Yeah. So I think. So I'll talk about the multi-hop QA as an example, but maybe it relates to vaguely, at least to vaguely, to what you're saying. So So let's say I have a model that tells me, or I have a way of sort of figuring out from the model's internal somehow that it's sort of paying attention to this piece of information here and this piece of information here, right? That somehow it's gotten here. But I really don't know what it does with that after that, right? I don't know. It could say I looked at these two, and I just checked whether those two are present, and then I only used this bit of information to decide what my answer is, right? That's not really multi-hop reasoning also, right? Because there is sometimes I need to apply a specific type of reasoning. So my frustration is sort of at a level where we can't even do the first bit, that actually to say that this model consulted these two bits of information in some way, just looking at the internals. I could write to this works that shows explanation is not, attention is not explanation, and when there's some back and forth on this stuff. So it's, we had, that was another weird thing that happened with the mobile stuff also. Like you can't really, even if you scale down the information to something minuscule level, the upper layers can still extract that information out. So it's very hard to do this stuff. So that's one frustration. The other for me is more that we are somehow thinking that just by building a data set, we would have given the model the right training pressures so that it has to do the right thing. That's totally not true, and we find so many weird ways in which the model can exploit these things. What I would like, so I'm a little bit skeptical on the interpretability side for the same reason that I don't know, I can't look at this and figure out if it does the right thing. So I want to go back and say, okay, let me do a behavioral study of these models. So if I change the input this way, if I fiddle it this way, then it has to do this thing. If it doesn't do this, then I know it's doing something bad. Right. So I don't know if that necessarily fits into the bottleneck kind of idea, but I'm stepping more away from actually having to look at the internals or sort of bake in inductive biases as a way to say, okay, it's going to do the right thing. I want to sort of come up with tasks and data sets where this kind of pressure, the right pressure is being executed, or use the models in ways that it actually does the right thing.
So in the future, you might be satisfied with some explanation of the neural network that doesn't have all that much to do with its internals.
I would be happy. So I think if I can predict its behavior, so my thing is, if the model gives me any explanation, then if using that explanation I change something about the input, then it has to be consistent with its explanation and do the right thing. That's the only way I think I can guarantee I trust its explanation. Yeah.
Very cool. Well, thank you very much.
Right. Thank you.